the moving components only go as far as is necessary, and that the computer always have a consistent model of the location of the workpiece and the material being worked on. DOS has sometimes been used as something like a real-time OS, and it sort of is in the sense that the application is the primary thing running. There's still interrupts, but the Sisters of Mercy, the band, used a DOS box as their drummer for years and years, so he apparently had at least that level of precision.
A free real-time operating system available. There's actually two of them. I don't have them both listed on this slide, but one is FreeRTOS. I cannot vouch for the quality of this project. I was just digging around online and found it. And another one I've seen cited in some books I've read is eCOS. It's lowercase e, C-O-S. And that's used as a learning example quite frequently. Now, if you do go the bare boards route, when you're developing your own drivers for the system on a chip architecture, if it's an interrupt-driven device, so you need to have a finer degree of control than just pulling it every once in a while. It usually means you're going to separate your driver into three parts. You're going to have an interrupt handler, which responds to interrupts like received byte of data to free up the data receive register and move it into a queue somewhere and then return to where it was in the program. You're going to have a low-level layer, which is going to have buffers and queues and have an application interface to that, and then you're going to have your application logic on top of that, which is going to decide what messages to put into those queues and how to parse the messages it receives. Now, I just kind of went through that.
Well, another option is not having an OS. On the smaller chips that I was waving around, there's no space for it and there's no need for it. It's very simple to access everything directly, so you don't need the hardware abstraction that an operating system provides, and there's nowhere to put it. The flash is just too small. Generally, a chip that's running software with no operating system works by having the reset interrupt start running the code that you have put on the chip immediately. So the chip powers up. When it powers up, the reset interrupt is called, and the reset interrupt handler does whatever initialization is required and then jumps to the beginning of the code. For those chips, they actually have a bootloader as well, which is a piece of code that allows reprogramming the chip on the fly. So you reset the chip. The bootloader waits for a message to come in telling it that it's going to be reprogrammed and then sending reprogramming data. If it receives that message within a certain amount of time, it'll write the new program into its flash memory and then jump to the beginning of that program.
The advantages to using a bootloader is it allows you to reprogram your device without having to open it up or possibly connect up a JTAG cable or a BDM cable and program it directly. You can do it via Ethernet, you can do it via serial or CAN bus or whatever communications bus you want, and usually the chip manufacturer provides some free assembly code which you can use however you want and modify however you want to put software into the application area of the memory. Now, when you start dealing with more complex projects, you're going to find that it makes sense to use more than one microcontroller. So you might have one 32-bit microcontroller that interacts with 5 smaller 8-bit microcontrollers, each of which connects to a peripheral device, like an actual mechanical device like a pump or a fan or some stepper motors, and needs its own logic, but it doesn't make sense to have all that logic in the larger chip, and some of that's for power reasons, some of that's for space and processing constraints. But the same object-oriented practices that you use in software design, you can also use with hardware design. So you might have several microcontrollers on a board, each connected to different pieces of equipment that are off-board.
Another example of object-oriented hardware is RF modules. RF engineering can get fairly complicated, as any RF engineers in the audience can probably tell you. But there are modules that have solved this problem. They're basically a small piece of circuit board that you can just plug into your board and supply with power, ground, and a digital signal, and they turn it into radio, send it some radio signal, send it out, and another receiving unit turns it right back into a clean digital signal. I found this immensely useful for a project I was working on that required remote control, because I didn't have to basically learn how to build a radio. I could just take this module, add it to the project, and essentially it's like a library. If you want to decode MP3s, people have already written libraries to do that. There's no reason for you to unless you really want to learn to decode MP3s. In this case, I didn't have time to learn all the RF engineering I would have needed to build this module, and so I could just use one that was already built for me.
Now, there's a couple communication buses that you can use. The CAN bus is typically used in auto or avionics applications and is very common on microcontrollers because of the wide industrial uses for it. So a CAN bus may connect your ECU of your car to a smart pedal, which is no longer it's no longer a mechanical push-pull cable, but it'll have its own microprocessor that's going to send a signal that has the position of your gas pedal and then translate that into a throttle command that it sends to the ECU controlling your car's engine. Now, they've got CAN protocol decoders that are built into digital logic analyzers and things so that you can decode CAN messages. You can buy PCI MCIA cards that have CAN buses on them, and basically it's inter-device communications when it's not used on the same board. SPI, which is known as a three-wire bus, is used between chips. Two-wire or I2C is also used between chips.
These protocols allow you to communicate with another IC that has a complicated functionality without having to use a whole lot of lines. A good example is temperature sensor ICs that support an I2C interface. The temperature sensor could be returning a 10-bit number that represents, say, the temperature above or below a certain set point or whatever. But you don't want to dedicate 10 full lines just for transferring the data, plus another line for telling it that you want it to transfer the data, plus your power, your ground, and the other signal that it might accept. So this bus allows you to have a two or three or four wire serial protocol between the chips, where one chip will tell another one what kind of configuration to go into or what sort of information it wants, and then the other one will send back the information serially, which saves a lot of time and saves a lot of circuit board traces, less wires connecting everything. RS-232 is also showing up more places than a 20-year-old protocol has any right to be showing up.
It's also used on the PCB to talk between multiple microcontrollers. So if you've only got two microcontrollers on the board, it'll be common to have an RS-232 channel between them, because at that point it's just two wires. You've got an RX line, a TX line, and it's not being shifted out to a port, but it may be useful to take that into account to see how to sniff the line.
It's a well-known protocol, and so it's very commonly implemented on chip. It's not uncommon to find an IC that has dedicated circuitry on it for doing RS-232 transmission and reception, just because it's easy to implement and everybody knows how it works already.
Other inputs to these microcontrollers are analog to digital inputs, which they translate a voltage value between 0 and 5 volts to either an 8-bit or a 10-bit value from 0 to either 255 or 1023, and then you multiply that by the proper divisor to turn that into, well, you multiply the 0 to 1024 to get your voltage value. And then based on what's connected to it, whether it be a thermistor, an RTD sensor for temperature, or pressure sensors or whatever, that's going to allow you to translate that voltage value into a actual value, whether it be in foot-pounds or however you measure that here.
PSI, degrees Fahrenheit or Celsius, depending on which side of the ocean you're on.
Another source of inputs are there's also high-speed inputs, which are capture devices. These can measure frequencies of signals. So if you've got, say, a tach sensor that's measuring the speed of a shaft, that's going to come in it's going to have a 1 for each time a dot on a gear goes past the sensor. And so it's going to create a PWM signal based on the shaft speed. So it's going to go up when it's across the dot and then back down again. And then the frequency of that will tell you how fast something's spinning. So for things where you're measuring speed, you might need a high-speed input. Or for controlling something, you might use a PWM output. And that is a pulse width modulated signal, which means you've got a period and a duty cycle. The duty cycle is how much of the period is actually at the 1 logic state and how much is at the 0 logic state. Because you could have a 1 millisecond period, but be at 1 for 1 microsecond or 999 microseconds.
Reverse engineering is becoming a more and more complicated legal topic all the time. In the United States, we have the DMCA, which is intended to prevent the distribution of circumvention devices for getting around copyrights, but is frequently used in what's called a SLAP suit, or a strategic lawsuit against public participation, to attempt to prevent someone releasing a tool that may or may not be used for circumventing somebody else's copyright. U.S. law is a local ordinance, but as we've no doubt found out, the laws are getting more and more restrictive everywhere. Reverse engineering shouldn't, in my opinion, be illegal, and I suspect that that's a commonly shared opinion, because it allows people to recover lost functionality of their hardware. A common example is the
hacking tools?
Well, yes.
Yeah.
But also there was a television recorder that had the ability to automatically skip commercials. They were sued off the market. The only way to get that functionality in a television recorder now is to build it yourself or add it to one that doesn't already have it, such as the more recent generation TiVos. Essentially, laws like this are damage, and they will be routed around, not only because people want their devices to do more, but in the name of simple capitalism. It's not the guy in the basement that the governments should be worrying about. It's the guy in the manufacturing plant in China who has found out that they can sell more units if they have more functionality in the unit. And so if the US can't manufacture a unit with commercial skip, or Germany can't manufacture a unit that might be used as a hacker tool, then they can manufacture it there, sell it, and now guess where the money goes? The process of reverse engineering hardware is very similar to that of software. You start with something that is a finished product, probably from someone else, probably that you didn't have design input into, and you have to figure out how it works and which parts of it are parts of interest to you for modification. You generally first break it down into subsystems, figure out what the parts of those subsystems are and what they're doing, and then figure out which ones you need to change to get the functionality that you want. In software, you would be opening something up, figuring out the various functions, and then figuring out which ones, say, do things like locking your MP3s so that you can't use them anymore, and replacing that with something that, say, immediately returns 0. In hardware, this could be looking for a line that is trying to determine whether or not a certain operation is permitted, and wiring it to high voltage or low voltage, depending on which one means go ahead and do it.
That could be involved in re-enabling the write line on a TSOP or flash chip, because sometimes they'll cut the trace for the write line to the on-chip memory, or not on-chip, but a memory chip that's also on the board, and by rewiring that you can enable yourself to be able to load whatever firmware you want into the device. And using the engineering process, you can, knowing the specifications of the chips, the interconnects, what pins are wired to what, you can arbitrarily create your own firmware if you know how all the chips on the board work and how they're connected.
I say the changes are optional because you don't necessarily have to be opening things up and learning about them to modify them. You could just simply be curious. That's how I got started in electronics, opening things up, figuring what does what, just because I wanted to know how things worked. And if, as an outgrowth of that, I happen to be able to repair things or improve them, then so much the better. Printed circuit boards, or PCBs, are the base part of any circuit. I have one here. This is the DEF CON speaker badge, and it shows